Welcome everyone to the last talk of the day. My name is Bahaa Naamneh, and I work for Crosspoint Labs, which is part of a private equity firm. So we mostly do private technical due diligence and stuff like this. But prior to that, I worked as a software developer for so many years in the Windows kernel space, so low-level stuff. And the talk today will be, sorry. The talk today, I will be talking today about the hidden risk of undocumented API documentation, and I will show you how software developers in pretty much all antivirus and EDR companies out there have overlooked a crucial Windows API behavior as a result, of insufficient or incomplete documentation from Microsoft. And as a result of that, they introduced a security vulnerability in their product. And as a bonus as well, at the end, I will show you that this same vulnerability was also present in other type of application other than antivirus and DDR. This is a disclaimer that I was asked to include in my presentation from my company. But to start with, let's discuss symbolic links, which will provide some context to the vulnerability I will be presenting in the talk today. I assume most of you are familiar with symbolic links, but if not, they are a link that references a named object, whether that's a file, folder, registry key, and so on. Now, symbolic links can pose security risk if not handled properly. And they have been exploited in various attacks like denial of service attacks and privilege escalations. And the vulnerability I will be discussing today belongs to this class of vulnerabilities. Now, symbolic links is a primitive that is available in all major operating systems, including in the Windows operating system, which is the one I will be focusing on today. Now, Windows supports several types of symbolic link types or links in general. So, for example, we have at the NTFS file system level, we have the NTFS symbolic links. So for those, you need to be an admin or authorized by an admin to be able to create such a link. And if you try to delete such a link using any documented Win32 API, like the delete file API, then only the link itself will be deleted and not the target, which is probably the behavior that you would be expecting. If you are reading and writing through a link, you would be expecting to read and write on the target. But when you are deleting, you expect to delete the link itself and not the target, at least in the default behavior. And this behavior, the delete behavior, is similar to other types of links in Windows. So it is similar to for example, the volume mount points, to directory junctions and hard links. The exception to that is the registry symbolic links, the one at the very end. So for those, it is sufficient to be a standard user, basically non-admin user, to be able to create such a link, unless you are trying to create the link at a location that the non-admin user does not have permissions to write and create a link at, like, for example, writing to the local machine registry hive. But what's interesting about this type is that if you try to delete that type of links using any documented Win32 API, using, for example, rig delete key, then the target will be deleted rather than the link. And that can have some security ramification, which I'll be discussing in the presentation. Now, registry symbolic links, if you are not familiar with those, this is a feature in the Windows registry that enables you to create a link from source key to a target key. Basically, you would mirror the target key at the source location. And they have been existing as part of the Windows registry for more than 30 years, so since the time of Windows NT. So it's not something new, but for some reason, this seems to be less known than other types of symbolic links in Windows. One example to that is the current control set, and I assume most of you have interacted with that registry key. And that is by itself is a link, and it redirects you to the key control set 001, which is the one you see on top there. And that's the last configuration or control set that Windows was booted with. It could also redirect you to other keys like control set 002, which is the last good known configuration that Windows was booted with. Now, if you try to view that current control set using the built-in regedit tool in Windows or any other registry link, those links will appear just like any other regular key, and there will be no indication that they are symbolic links. So you won't be able to tell the difference between a registry key and a registry link, using regedit at least. You would need to use other tools like the one I'm using here, Total Registry, to view the underlying structure of the registry link. And the registry link is pretty simple. It is still a registry key, but it is an empty registry key that has one value, named symbolic link value, and has the type break underscore, and its value is the absolute native path of the target key. So in the case of current control set, the native path will be registry machine system control set 001. Now, if you want to interact with those registry links programmatically, Microsoft does provide some information as part of the documentation that deals with creating and opening registry keys. But that documentation is insufficient and has several issues, but I will not be covering this today. What I will be covering today is the delete action on the registry keys or registry link. But before we jump into the details on that one, let's just see how Microsoft document the delete action on types other than the registry symbolic links. So for example, we mentioned the NTFS symbolic links, and there, as part of the delete file API, they clearly document the behavior of that API if it's invoked on an NTFS symbolic link. So they tell you there, if the path points, which is path that is passed to the delete file, points to a symbolic link, then the symbolic link is deleted and not the target. So it's very clear. Similarly, they tell you if you want to delete a hard link, then you can use the function or the API delete file. And if you want to remove directory junction, you can use the remove directory. So you get the point here. They have documented somewhat whether what API to use in order to delete certain links, or what would be the behavior if you invoke an API on a link type. However, this is not the case for registry symbolic links. So for those, you will not find any information in Microsoft documentation that tells you how to deal with registry symbolic links. They don't document either what APIs to use or what would be the behavior of APIs that deals with deleting registry keys when they are invoked on a key that happen to be a registry symlink. And that include documentations for APIs like regdelete key, regdelete tree, and even the native versions of those. And that can be a significant concern, because when a software developer turns into this documentation, they may overlook the importance of handling registry symbolic links. So if you don't have information about that, as a software developers, you might actually not think about that you need to deal with this situation or an edge case. Now, to make things worse, it's not like only the documentation is incomplete, but also, as I mentioned, the behavior of Win32 APIs that deals with deleting registry keys behave strangely or not in accordance with how things are done on other types of links. So typically, if you want to delete a registry key in Windows, you need to open that key and obtain a handle to it, and then you pass on that handle to other APIs to perform the delete action on them. Now, if your software opens a key that happens to be a link and it does not specify the option reg option open link and then pass on that handle to reg delete key or reg delete tree, then the target will be deleted. Similarly, what's even more interesting is that even if your software was aware that the key is a link and it opens it with the option reg option open link, those APIs would still delete the target rather than the link. So basically, if you are a software developer in the user mode, you are left with no documented API to delete registry link. The only option for you to do that is by using the native API anti-delete key. But the problem with that is that it is an undocumented API, and you have to explicitly import that from NTDLL library. Okay? Otherwise, you will risk deleting the target again. If you are operating in the kernel mode, you will have to use the native ones. But again, every single time you want to delete a key, you have to check if that key is a link or not. And if so, you have to open it with the option, reg option, open link. Now, this behavior, the one I mentioned here, creates or leads to a situation that creates a mismatch between what a programmer intends and what is actually deleted by Windows. So basically, as I'm phrasing here, what you see is not what you delete. And that can lead to a security vulnerability if a non-privileged attacker, basically one that is running as in the context of non-admin account, can trick a privileged process to follow that link and then lead it to delete a restricted or a protected registry key that the non-admin user does not have permissions to delete it in the first place. Now, in most cases, this is not an issue because privileged processes, they would either impersonate, so if they are running as system, they would impersonate the currently logged in user, basically lowering their privileges before they perform an action like a delete action on a key that is in unprotected location. Or they simply don't delete keys in locations that are in unprotected locations. However, there are certain types of application like antivirus and EDR agents that their objective is to remediate and delete threats that are detected, including malicious keys or unwanted keys. And they do so even if that key is in unprotected location. And to achieve that goal, if they want to lower if they want to impersonate the currently logged in user, so if they are running a system and they want to lower their privileges to user, that will be safer for them, but might be insufficient to get rid of the malicious key. So what they do, they go at the unwanted registry key with their high system privilege, and they try to remove that, which exposes them to security risk if that key happened to be a link and they fail to check that prior to deleting it. Now, this is the vulnerability, but I will be talking a little bit about the risk of that vulnerability. But the vulnerability itself, I initially found this during a security assessment I did on one specific antivirus product. But when I realized how insufficient the documentation was around the whole topic of registry symbolic links, I knew that other vendors must be also vulnerable to that. And sure enough, with the help of colleagues and friends, we were able to test 18 vendors. And we found out that apart from 2, they all were vulnerable to this issue. Since then, they have all patched their products, but we are unable to test all the products on the market. So it is likely that some other vendors that we haven't tested, they are still vulnerable to this issue. Also, I should mention that my research was focused initially on AV and EDR, but there is a chance that there are other applications are also vulnerable to this issue. And I will show you at the very end an example for application other than antivirus and EDR that are vulnerable to this issue. Now here I would like to talk a little bit about the process I went through to identify the actual security risk behind this vulnerability. And the idea is that I want to find a location that a non-admin user can create a link at and then trick a privileged process to follow that and delete a protected registry key. And if you are familiar with the Windows registry, you know that there are several registry hives. So the main 2 ones is the current user registry hive and the local machine registry hive. So my assumption was at the beginning that the current user registry hive is owned by the current user, currently logged in user. And I assume that all keys under that are accessible and writable by the current user. But I wanted to double check that. So I used the tool access check from sysinternals to try to find if there are keys within the local machine, within the current user registry hive, basically HKCU, that the current user have only read-only access to, meaning that they are protected for one reason or the other. And I came across a couple of interesting ones. The first one is the second line from top, which is the registry key where the browser edge stores the path to a manifest file that specifies the path for an executable that belongs to the native messaging host, basically an executable that facilitates the communication between trusted extensions that runs within Edge and the host system. And it is possible to man in the middle of that process, but that will be out of the scope for today. What I'll be covering is the second interesting registry key, which is the one highlighted in yellow in the middle of the screen, which is HKCU software policies. But before we go into the details on that one, I just want to mention a couple of things here. First, Windows does not allow you to create links across different registry hives. So you cannot create one from the current user registry hive to the local machine registry hive for security reasons. And the second thing I want to mention is that I tried to run the same exercise where I run access check to find the opposite thing on the local machine registry hive, which is the protected registry hive. To try to find if there are registry keys within that the non-admin user have permissions to write to, basically to create links at. So I found a bunch of those, but none were interesting in the context of AV and EDR, meaning even if I was able to create a link there, it would have been difficult for me to get the AV or the EDR to delete that location. It might be possible, I just didn't spend enough time looking into that. Now, back to that current user software policies registry key, and that is the location where Windows stores the local group policies for the currently logged in user. And in Windows, only admin accounts are authorized to configure local group policies. Non-admin users are not authorized to do so. So if you happen to have maybe a corporate Windows laptop, you probably are assigned a non-admin account onto that. So, and if you try to run, for example, gpedit.msc, you probably will see an access is denied because you as a non-admin user should not be allowed to configure group policies, even the local ones for your own user. Similarly, if you try to view the permissions on the policies registry key, you will see you only have read-only access. Now, there are thousands of local group policies that you can set as part of those local group policies, including from Microsoft and other vendors. So it is imperative on Windows to secure that location because otherwise, an attackers, if they are able to configure local group policies, they will be able to gain additional capabilities and permissions on the system that you don't want to give them that. And here is one example for a group policy that you can set as part of those local group policies. It's called always install elevated. And that's a policy that enables non-admin users to install Windows package installer with elevated system privileges. Basically, it will give the non-admin user an ability to install MSI installers without having to enter an admin credentials. So typically an admin would give this to users so they are not bothered by them asking for credentials every single time they want to install an MSI installer. Now this is a very risky policy to set, and Windows requires it to be set on the local machine hive and also per each user you want to enable this policy for. And attackers have been abusing this by basically if a malware running on the system, they will query the registry and see if it's set per local machine and per user, and if so, they will run their malicious code as an MSI installer, and this way they would elevate their privileges from non-admin user into system without needing any vulnerability. So it's not something that you would want to set. Now imagine the case where this has been already set per local machine, but it's not set for the user. And we will see how we can exploit the vulnerability, the registry symbolic link vulnerability, to enable this also per user. And here is how the attack goes. So we have an attacker running in the context of non-admin user. So regular user. So what they can do, they can create a symlink, registry symlink under the current user registry hive, and they would create that under a location that they know that a vulnerable privileged process would be deleting along with the link itself. And the link itself will be pointing to the policy's registry key, which is a read-only policy by default. In the second step, the attacker would either wait or trigger the privileged process to delete that location along with the link. Now, the privileged process, if it's vulnerable, would be thinking that they are deleting the symlink itself, but in reality, they will end up deleting the policies, because that's how rig delete key works in Windows. It deletes the target by default and not the link. Okay? Once that has been deleted, what the attacker can do, they can recreate the policy's registry key, but this time recreated with permissive write permissions, so read and write. And they can do so because they have enough permissions on the parent registry key. Now, since you have write now access to the policies, you can set whatever local group policies you want, including the always install elevated. And once that has been set, you can just run your malicious code as an MSI installer, and that would basically elevate the attacker privileges from non-admin to system, which basically you have access to that. I have a short demo here, a recorded demo that basically shows this attack. So I have a Windows 11 running a standard non-admin user, and I have a vulnerable antivirus, and I'm just hiding the identity of the antivirus because there were so many of them that are vulnerable, and I didn't want them to blame me for picking up on one of them. So here you can see that I have a medium integrity, which is the non-admin integrity. And I have a demo here that the first thing my demo is doing is just validating the default configuration. First thing, I'm going to run an MSI installer, which is called cmd.msi. And by default, this should run as a regular user, not a system. The MSI installer will launch as cmd.exe. And if I run who am I into that, you will see that it's running as limited, which is the default, without any elevation. Then I'm just verifying that I indeed have read-only permissions on the policies registry key. And if I try to write or delete it, then I'm gonna get an access is denied. And that's the default behavior. Then in step number 6, I'm basically running my exploit here. And the exploit is, as I mentioned in the attack before, I'm creating a link and pointing that link to the policies registry key. And I'm creating this at a location that, if you are familiar with antiviruses, they have, when a malware, some malwares, they would create malicious registry key. Basically, would create registry keys within the registry. And all of the antiviruses have a list of known bad registry keys. So what my exploit would be doing would be intentionally creating a malicious or something that would look as a malicious registry key to the antivirus. So when the antivirus is scanning the registry, they will pick up that and try to delete it. But I will be configuring that as a link. So I have here created that link already. And the way I'm triggering the antivirus is by simply running quick scan here. I could have also waited for the antivirus to just scan the registry. And it is running in the background here. It is running in the background, and soon enough, you will see that it deleted the try to delete the link, but it will end up deleting the policy. So my demo here, .exe, is just waiting for that policies to get deleted. So here we have it. The policies was deleted, and then I recreated that. Once it has been deleted, I can recreate it with write, and then I'm able to. Oh, sorry. Now I have write access, and then I can run add the always install elevated, and if I run the same MSI installer from before, it will run cmd. Who am I? And now you see here we got system on the system on the. Yes, so that is the first demo. Oops. Okay, the second attack vector, and this is very specific to antivirus and EDR. The first attack vector, it's a more generic attack. It can be applicable to other types of application other than AV and EDR, but this one is very specific to AV and EDR. So when you install an antivirus or an EDR agent in your system, it will install itself as a system service. And that means that it will add itself under the current control set services. And if an attacker is able to delete that registry key that belongs to the antivirus, and then you reboot the system, then basically you disable the antivirus. So what antiviruses and EDR do, they implement something called anti-tamper protection. Basically to protect their own registry keys, files, and so on, because you don't want an attacker, even the one that is running as an admin, to delete their own registry keys and disable the antivirus this way. But what an attacker can do, can bypass that anti-tamper protection by, again, creating a symlink, but it's going to be pointing to the antivirus registry key, and then they will trigger or wait the antivirus, and the antivirus will think that they are deleting the symlink, but they will end up deleting their own registry key, the one that is basically telling Windows how to run their system service. And that would work because their anti-tamper protection is not enforced on their own processes. And now once you reboot the system, basically you will disable the AV or the EDR. And using this exact technique, I was able to disable a very known EDR agent. And once I have rebooted the system, the UI component of that EDR agent popped up and telling me that the endpoint security agent is not running because the core system service was no longer running on the system. Now, just to recap the security impact of this vulnerability. First, none or attackers running in the context of non-admin user can configure group policies that would otherwise be inaccessible to them. And that would, through that, they will gain additional capabilities and permissions on the system. And as an extension to that, they can also escalate their privileges from non-admin to system in some cases, like the always install elevated that I've shown before. Second thing, you can disable security products like antivirus, EDR, firewalls, and so on. And there are probably more security impacts, depends on what registry key the attacker is trying to take advantage of. You can break the entire system, like getting into a indefinite blue screen by, for example, deleting a very critical registry key that Windows will not be able to load without it. Now, how did this bug surface and who is it to blame with it, really? Now, it is tempting to blame the software vendor, especially if that software vendor happened to be an antivirus product. But in reality, when you examine the underlying causes of the issue, you will see a number of unfortunate factors. So first, we have an unexpected behavior in the way those APIs that deals with deleting registry keys behave on Windows in the way that they delete the target rather than the link, which is not the expected behavior when you are dealing with deleting a link. And that basically formed the foundation of the problem we have here. Secondly, we have inadequate documentation from Microsoft that failed to warn about the risk of handling registry or deleting registry link, which I believe was a core factor in the problem's development. And lastly, some responsibility must also be placed on the software vendors for not having tested their product sufficiently. But in my opinion, there was a combination of different risks that led to pretty much the entire industry of AV and EDR making the same mistake, because we found out that pretty much all of them have fallen into this same mistake. And in my opinion, if the documentation was a little bit more comprehensive and telling the software that you need to pay attention to that, they might not have made that error. Now, as I mentioned initially, my initial research was focused on AV and EDR, but the vulnerability itself can be and is applicable to other applications. And here I'm going to give an example to that. So what is common to Google products that have native application that run on Windows, for example, Google Earth or Google Chrome, and other browsers that are based on Chrome like Opera, Brave, Edge, and even non-browser application like Dropbox. They all use the same installer or updater called Google Omaha, developed by Google. And that Google Omaha runs in its own process. Typically, it's called Google Update.exe, and it runs as a very privileged process in the context of trusted installer account. And that's basically is responsible for three things: installing the application, updating the application, and uninstalling the application. Okay? And what I found when I looked at this, I found three issues with this. First, it does not handle deleting registry symlinks. Now, by itself, it's not an issue, even if it's in a privileged process. But when it becomes an issue, when you are dealing with, when you are facing issue number 2 and number 3 here. And number 2 here is that this privileged process delete keys in the current user registry hive from a privileged process, and those keys can be in unprotected locations, meaning that the attacker can create a link there and pointing the link to a privileged or a protected registry key, like the policies registry key I was talking about. So that is the second issue. The third issue is the more critical issue, is that they create a key under the local machine registry hive, which is the protected registry hive. And that's the code on the right side that shows that the key they create, it's called client state medium. And what they do is that they override the default privileges of that key, where they allow non-admin users to write to it, meaning that you can also create links under that key. And if you are able to create a link under that key from non-admin user, you can point it anywhere in the local machine registry hive, and basically you will end up deleting or causing that installer or uninstaller to delete something the non-admin user should not be allowed to do so. Now, what I reported that to Google, obviously, and they have fixed the issue by deleting registry symlink instead of the targets when deleting registry keys. So they would check if the key is a link, and if so, they would delete the link rather than using the default API behavior. So basically what they did here, they fixed number 1. But that fix is incomplete or can be risky, because the delete is one issue, but also writing through registry symlink can be an issue. Luckily, they are not vulnerable to the write through link, but they were vulnerable through delete through link. So they fixed number 1. And that subsequently fixed the issue number 2 and number 3 for their specific case. Now, they made 2 fixes, one on Google Chrome and one on Google Omaha. Google Chrome is using slightly different version of Google Omaha, but it's pretty much the same code base. And here at the bottom, I took a snapshot from the comment that they made, where you can see that they had to use the undocumented API anti-delete key. And they say in the comment, declare anti-delete key since no official header has it. And that's the problem, basically, from Microsoft, because they are not providing a good way to delete or support deleting registry links. So you, as a developer, you will have to use undocumented APIs to implement things correctly. Now, the issue, to exploit these issues in Google updater or installer, whatever you want to call it, the user must uninstall the application in order to get the registry key to be deleted, and then, delete the link and then what it is pointing to. But how likely this is to happen? I mean, once you install Google Chrome or Google Earth, it's rare that you would end up having to uninstall it or reinstall it. But what a malware can do, they can force the user to reinstall the product, the affected product. And they can do so by causing the application to display a fake error message upon loading, and then suggest to the user to uninstall it or reinstall it, and then terminate. Now, typically, you shouldn't be able to do that. Like, you cannot, a malware running in a non-admin user, they shouldn't be allowed, they shouldn't be easy for them to get Google Chrome or Google Earth to display an error like this, because that's tampering in their code. But what the attacker can do, they can combine the registry vulnerability with another attack. For example, a DLL side loading attack, where you get the application to inadvertently load another DLL to do what you want here, which is display a fake error message that would suggest to the user to terminate and then terminate the application. And I found a vulnerability like this in Google Earth, and I will be demoing this shortly after this slide. You can also, for the malware, they can also, for example, manipulate the desktop shortcuts icons. So basically, you cannot delete Chrome icon on the desktop, but you can moving away from the visible screen and then put another icon that points to an application that basically all it does is just displaying that error message and then terminate. From the user perspective, it would look like as if Chrome is terminating for no good reason, and then you will have to reinstall it. So the first demo is that Google Earth DLL side learning, which is like, if you think of it, is the first stage in the attack. You exploit this just to get the user to uninstall the application, and then the second stage, you will exploit the registry vulnerability. So when you install Google Earth, and here I'm installing, have installed it, it will install itself under the program files folder, which is a protected folder. So non-admin users should not be allowed to write into that. So you cannot tamper with it. But what is interesting is that when Google Earth loads, it loads a DLL called Swift.dll. It loads other DLLs this way, but what's interesting about this is that it loads this with the file name only. So it does not specify the full path, which means that what happens is that when you do something like this in Windows, Windows will look for that DLL in the current folder of the application. So in this case, in Google Earth, if it does not find it, then it would search in the DLL search order of Windows, which is a predefined folders that Windows would query to try to find that DLL. So for example, it will first try to search for it in System32, in Windows, and so on, until it gets to a point where it looks for that DLL into the folders that are specified by the path in environment variable for both system and user. And that path includes this folder, users limited app, Microsoft Windows apps. And this folder, for a non-admin user, is a writable folder, meaning that you can place, if you can see here the permissions on this folder, you'll see you have full control over this folder. So what a malware can do, they can basically place that Swift.dll into that folder. And then when you run Google Earth, it will try to load Swift.dll. And again, as I mentioned before, that DLL will just simply display a fake error message. So in this, showing to the user, it's a critical error and you need to uninstall and then reinstall the application to resolve the issue. So that way, a malware can actually force a user to reinstall the application, and then they can exploit the second stage. And this is a demo of a second stage. And in this demo, I'm creating a registry. I'm creating a registry link that is pointing to the filter manager service, which is a very critical service to Windows. Without it, it will not run. And I'm creating this from non-admin user under this client state medium, which I mentioned before, which they override their privileges to allow non-admin users to create links at. Okay. And once I have done that, now from the user perspective, they would run Google Earth. They will be greeted with this error message, the fake one, suggesting to them, oh, you should reinstall the application because we are unable to run it for no apparent reason. I'm just going to skip quickly here. So the user will go ahead and try to uninstall it. Of course, you need an admin account for that. And then they try to install the application. It stopped for some reason. I think I need to rerun the application, the video again. So I'm just, as a user, trying to reinstall the application. And during that process, the filter manager here, which shortly will disappear. So Google Earth end up deleting the filter manager service. What does that mean if you reboot the system now? Since it's a very critical service, you will end up having a blue screen. And that's going to be a permanent blue screen. Every single time you reboot the system, you'll end up in this situation. Another demo, which is in this case, is exploiting Chrome to disable the Windows firewall. So it is similar to the first demo I showed on the antivirus, where I'm creating a link, but this time I'm pointing the link to the BFE service, which is the base filtering engine service. So all firewalls that are implemented on Windows, they rely on this service from Microsoft, which is a filtering framework that enables firewalls to create rules and so on. So I'm just creating the I think I may have skipped one part, or Oh, here. At the beginning, you see that the firewall is on. So I'm creating the service. This is just a process monitor just to view the events. And installing Chrome. We'll see all of a sudden Google update.exe is touching or performing actions on BFE service, and that's not something it should do. And if we filter by reg delete key, we'll see that it's even deleting the BFE service, which should never be happening. If we refresh now, the BFE service should be gone. And then if we reboot the system, you need to reboot the system because Windows would look at this registry tree every single time it boots the system and see if it's there, it will run it. Now you see here that the firewall is having some error message there. And if we run the Windows Security console, which is like the modern control panel, we'll see we are struggling a little bit to get information about the firewall, but soon enough, yeah, there you have it. So there's an error message, and here, if you remember, the firewall is no longer on anymore. And if you try to restore the settings, even as an admin, you will never be able to recover from that because Windows does not have information about how to recover from something like this. And that way, basically, I disabled Windows Firewall through an installation of Chrome. Okay, that's the demos I have for today. Now, some practical tips if you are a software vendor and you are writing application is that first you should review your code to ensure it does not allow deleting or writing to privileged registry key via registry symlink manipulation. And the second thing is that you always should use user impersonation when accessing unprotected registry keys or object in general from privileged processes. So if you are running as a system service, it's important to impersonate the currently logged in user, basically lower your privileges and perform the action as if the user had performed that on unprotected objects. You should always set the correct access control list on your created registry keys, and you should never do something like what Google has done, override the access control list to enable write access to non-admin users. And finally, some key takeaways. So registry links can pose security risk if not handled properly, and you should be careful around how you are deleting registry links and how you are dealing with those. But the main key takeaway is the one in blue here, is that if you writing an API documentation, then you should probably include potential security risk if you are aware of those, obviously, to promote secure coding practices and reduce the likelihood of security incidents, because software developers relying on your API are always, familiar with all the intricate details of your API behavior and what could happen if I do this or I forget to do that. So if you can help them to guide them through how to properly use your API and what to be careful about, that can absolutely increase or promote secure coding practices. Yes, that was all. Yeah, thank you.